Have you ever opened your chemistry textbook to the organic section and just felt completely lost? I mean, there are millions of carbon compounds, and they all seem to have these crazy long names. It feels like you're supposed to memorize a dictionary. Well, what if I told you there's a system, a kind of family tree for carbon compounds that makes everything click into place? Today, we're going to crack the code on what's called the Homologous Series. Trust me, this is the secret to finally taming organic chemistry. Okay, but before we get into the nitty-gritty, let's talk about how to make sure this stuff actually sticks in your brain. You know, listening is great, but doing is how you really learn. So, do me a favor, pause for just a second, grab your phone and scan this QR code. It'll take you to MCQSPM.com. After this explainer, you can go there and try out some real exam-style questions on this exact topic. It's a total game changer. All right, you ready? Let's do this. So here's our game plan. First, we'll get the big picture with carbon's family system. Then, we'll meet the most important families, the hydrocarbons. After that, we'll learn their secret naming code. And then, the best part, we'll use all that to crush a real exam question. Finally, I'll send you off with a little mission. Sound good? Let's jump in. Right, so Section 1, this is all about the secret weapon that chemists use to keep all these millions of compounds organized. This isn't about memorizing lists, it's about understanding the logic, the beautiful system behind it all. Let's be real for a second. This is the challenge, right? Millions of compounds. If you had to learn about every single one, well, you'd never finish. It's why so many of us feel overwhelmed by this topic. But here's the thing. Chemists are smart and maybe a little lazy. They don't study them one by one. Nope, they group them. And that brings us to the hero of our story today, the Homologous Series. Just think of it as a family of chemicals. It's a whole group of compounds that have similar structures, they react in similar ways, and they follow a really predictable pattern. So here's the magic trick. If you understand one member of the family, you pretty much understand them all. So what exactly makes them a family? Well, first, they all share the same general formula. That's kind of like their family DNA. Second, they all have the same functional group, which is like the family's last name. It's what gives them their identity. Because of that, they all have really similar chemical properties. And just like siblings, each member is just a little bit bigger than the one before it, specifically by 1 carbon and 2 hydrogens. This means their physical properties, like boiling point, just increase nice and smoothly as you go down the list. See? It's a system. Okay, now that we get what a family is, let's meet the most famous families in the neighborhood, the hydrocarbons. As the name suggests, they're made of just 2 things, hydrogen and carbon. They are the absolute bedrock of organic chemistry. First up, we've got the alkanes. I want you to picture a carbon-carbon bond as a handshake. Alkanes only have single bonds, so they're only doing single handshakes. This means every carbon atom has plenty of free hands to hold on to as many hydrogen atoms as physically possible. That's why we call them saturated. They are completely full, totally saturated with hydrogen. Next up, the alkenes. These guys are a little different. They have at least one double handshake, a double bond between 2 carbons. Now, because those carbons are using more of their bonding power on each other, they can't hold as many hydrogens. And that's why we call them unsaturated. They're not full. They could potentially hold more hydrogen if that double bond opened up. And you can probably guess what's next. The alkynes. That's right, they have a triple handshake, a super strong triple bond between 2 carbons. This makes them even more unsaturated than the alkenes because they're holding on to even fewer hydrogens than they could be. And this table right here, this is your new best friend. It puts everything we just talked about together. Just look at the general formulas, the family DNA. See that beautiful pattern? For every handshake you add, from a single to a double or a double to a triple, you lose 2 hydrogens. CnH2n plus 2, then CnH2n, then CnH2n minus 2. This table is your cheat sheet. Burn it into your memory, and you've got a huge piece of the puzzle solved. Okay, we know the families, but how do we give each individual member a unique name? For that, there's a system called IUPAC. Now, don't let the name scare you. It's not a bunch of boring rules you have to memorize. It's more like a simple, logical code. Once you learn the 2 parts of the code, you can name pretty much anything. The entire code boils down to this: a root name plus a suffix. That's it. The root name just tells you how many carbons are in the chain. It's a simple count. The suffix, well, that's the family's last name we were talking about. It tells you if you're looking at an alkane, an alkene, or something else. Let's look at that first part, the root name. This is really just a bit of vocabulary. 1 carbon gets the root meth, 2 carbons eth, 3 is prop, 4 is bute, 5 is pent, and so on. This part is just about counting carbons. And here's the second part, the suffix. This is the part that tells you the family. If it's an alkane, the name is going to end in ane. If it's an alkene, it's going to end in ene. An alcohol? That ends in all. See the pattern? The ending of the name tells you what kind of molecule you're dealing with. All right, let's put the code into action. Let's say we have an alkane, and it has 3 carbon atoms. We just look at our tables. The root for 3 carbons is prop. The suffix for the alkane family is ane. You just stick them together and boom, you get propane. It's that simple. And we can even double check with our general formula from before to find its molecular formula is C3H8. It all connects.
So the theory is cool and all, but the real test is whether you can use it when the pressure is on, right? In an exam. So let's take a look at a real past paper question, and I'll walk you through not just how to get the answer, but how to think your way to the answer.
Okay, here's the question. We've got 2 different hydrocarbon molecules. The question asks which of their properties is most likely to be similar. Now, the options are usually things like boiling point, density, maybe solubility. So how do we figure this out? Okay, I want you to pay close attention here because this is the #1 trap students fall into. They see 2 different molecules and they immediately think about things that change with size, like boiling point. I mean, it makes sense. A bigger molecule is heavier, so it'll have a higher boiling point. But the question asks what's similar. That's a huge clue that we need to be thinking about a property that's based on their chemical type, not their physical size. So here's how you break it down like a pro. Step 1, identify. What kind of molecules are they? They're both hydrocarbons, and a key fact about hydrocarbons is that they are non-polar. Step 2, recall the rule. What's the golden rule for solubility? Like dissolves like. Polar things dissolve in polar things, non-polar things dissolve in non-polar things. Step 3, apply that rule. Since both of our molecules are nonpolar, they are going to behave the same way in solvents. They'll both dissolve in nonpolar solvents, and neither will dissolve in polar ones like water. And finally, step 4, conclude. The property that's going to be similar is their solubility. See? Simple, logical, and you avoid the trap. Wow, we've covered a ton of ground, from the big idea of families all the way to exam strategy. But the real goal here is for this knowledge to stick with you, to be more than just something you spit out on an exam. So let's wrap this up. All right, let's do a super fast recap. What do you need to remember? 1, homologous series are just families. 2, their last name, their identity, comes from their functional group. 3, their full name is just root for the carbon count plus suffix for the family type. 4, all hydrocarbons are nonpolar, so they have similar solubility. And 5, and this is the most important one, practice is everything. So make sure you visit mcqspm.com. And I'll leave you with this little mission. This stuff, chemistry, it's not just in a textbook, it's literally all around you. That sweet, fruity smell from a candy, that's from a family called Esters. The sharp smell of vinegar in your kitchen, that's a carboxylic acid. You now speak the secret language of these molecules. So my question to you is, what other chemical families can you find in your world today? Keep asking questions, stay curious, and you'll start to see chemistry everywhere. Thanks for tuning in.